Now we are going to look at another important application of derivatives, which is motion along a line. This idea appears often in physics and engineering, but it is also a very helpful way to understand derivatives. Let S of t be the position of an object at time t. So S of t tells us where the object is located along a line at a particular time. The velocity of the object at time t is given by v of t equals s prime of t. This means the velocity is the derivative of the position. In words, velocity is the rate of change of position. So velocity tells us how fast the position is changing and also the direction of motion. Next, we define speed. The speed of the object at time t is given by the absolute value of v of t. This means we take the absolute value of the velocity. Speed only measures how fast the object is moving, but it does not include direction. So we say speed is the magnitude of velocity. Next, we define acceleration. The acceleration of the object at time t given by a of t equals v prime of t equals s double prime of t. This means the acceleration is the derivative of velocity, or the second derivative of position. So acceleration measures how the velocity is changing over time. In other words, acceleration is the rate of change of velocity. Now, let's work through an example. The position of a particle moving along a coordinate axis is given by s of t equals t to the third minus 9t squared plus 24t plus 4 with t greater than or equal to 0. This means the function tells us the position of the particle at time t. First, we want to find the velocity function. Remember that velocity is the derivative of position function, so v of t is s prime of t. So we take the derivative of s of t, differentiate each term. Derivative of t to the third is 3t squared minus the derivative of 9t squared is 18t plus the derivative of 24t is 24 and the derivative of 4 is 0. So the velocity function is 3t squared minus 18t plus 24. Question B. At what times is the particle at rest? A particle is at rest when its velocity is 0. So we set the velocity function equal to 0. This gives 3t squared minus 18t plus 24 equals 0. And we solve this equation for t. This is a quadratic equation. When we have a quadratic equation, we can solve for this by factoring or by using quadratic formula. If the expression is factorable, it is much faster to solve by factoring. So we will try to factor this expression. First, we can factor out a 3. Now, we can factor this expression. T squared minus 6t plus 8 factors as t minus 2 times t minus 4. We set t minus 2 equal to 0 and t minus 4 equal to 0 to solve for t. From this equation, we'll add 2 to both sides to have t equals 2. And from this equation, we add 4 to both sides to get t equals 4. So the particle is at rest when t is 2 or t is 4. Question C. On what time intervals is a particle moving from left to right and from right to left? Now we want to determine when the particle is moving from left to right and from right to left. To do this, we look at the sign of the velocity. If the velocity is positive, the particle moves to the right. If the velocity is negative, the particle moves to the left. From the previous step, we know the velocity is 0 when t equals 2 and t equals 4. These 2 points divide the timeline into 3 intervals. And the 3 intervals are from 0 to 2, from 2 to 4, and from 4 to infinity. Now we check the sign of the velocity in each interval. When t is in between 0 and 2, we want to know if the velocity is positive or negative. So let's pick a number in between 0 and 2. Say I pick a number 1. This is the factor form of the velocity. So if t is 1, I'll have 1 minus 2, which is negative, 1 minus 4, which is negative. I'll have 3 times negative is a positive. When t is in between 2 and 4, we want to know if the velocity is positive or negative in this interval. So we pick a number in this interval, say we'll pick 3, and we plug 3 into this velocity. 3 minus 2 is positive, 3 minus 4 is negative. Positive times negative is negative. When t is in between 4 and infinity, again, we want to check the sign of the velocity. So pick a number in this interval. Say I pick 5. 5 minus 2 is positive. 5 minus 4 is also positive. Positive times positive is positive. So the particle moves to the right in this interval, moves to the left in this interval, and moves to the right in this interval. Now let's complete part D. The question asks us to use the information obtained to sketch the path of the particle along a coordinate axis. Before we draw the motion, we first need to know where the particle is located at some key times. In particular, we want to know the position when the particle starts moving, which is at t equals 0, and the position when the particle changes direction, which happens when the velocity is 0. From part B, we already found that the velocity is 0 at t equals 2 and t equals 4. So these are the times when the particle changes direction. Now, let's compute the position of the particle at those times. First, we need to find the position at t equals 0. Remember, our position function is s of t equals t to the third minus 9t squared plus 24t plus 4. Now, substitute t equals 0. We get s of 0 equals 0 to the third minus 9 times 0 squared plus 24 times 0 plus 4. That simplifies to 4. So the particle starts at the position 4 on the coordinate axis. Next, we find the position at t equals 2. Substitute 2 into the function. We get s of 2 equals 2 to the third minus 9 times 2 squared plus 24 times 2 plus 4. We get 24. We get s of 2 equals 24. This means that at time t equals 2, the particle is located at the position 24. Now, we find the position at t equals 4. Again, we substitute into the function. We get s of 4 equals 4 to the third minus 9 times 4 squared plus 24 times 4 plus 4, which is 20. So s of 4 equals 20. This tells us that at time t equals 4, the particle is located at position 20. Now, let's sketch the motion along the coordinate axis. First, draw a number line representing the position s of t. This number line represents the position s of t. Now, mark the important positions at 4, 24, and 20. The position is 4 when t equals 0. The position is 24 when t equals 2. And the position equals 20 when t equals 4. From part C, we determine that the particle moves to the right when t is in between 0 and 2. The particle moves to the left when t is in between 2 and 4. And the particle moves to the right again when t is greater than 4. Now, we start at the position 4 when t equals 0. The particle moves to the right when t is in between 0 and 2. At t equals 2, the particle stops momentarily and changes direction. At t equals 4, the particle again comes to rest and changes direction. So, the motion of the particle can be described like this. The particle starts at position 4, moves to the right until it reaches 24, then turn around and moves to the left to position 20, and finally turns around again and continues moving to the right. This path is exactly what is shown in the diagram. By analyzing the velocity function, we were able to determine both positions where direction changes and the overall motion of the particle along the line.